Welcome students, welcome to the computer science class. In this tutorial, we will learn about number system. Now, the term number system, what does a number system mean? It is a system of representation of numbers. Broadly, number system can be of two types, can be categorized into two types. One is positional number system, another is non-positional number system. The one used by early men were the non-positional number system, where they used an additive approach to represent numbers. They used sticks, pebbles, or some objects. They accumulated those sticks and pebbles, and they used to count those pebbles to represent a number. Like if they want to represent number 5, they has to represent it with 5 pebbles. If they want to represent the number 50, they have to represent the number with 50 pebbles. So each pebble accounts for only a value 1. So there is no other value than 1. There is no value with respect to the position the pebbles occupied in the presentation, right? So this is called a non-positional number system, and such a number system you can well assume is very hard for arithmetic calculations. We cannot do arithmetic calculations with a non-positional number system. So as men grew, man evolved, man started using positional number system. And what kind of positional number system we use in our day-to-day life? We use the decimal number system. The number system having 10 digits, that is 0 to 9. So we represent the magnitude of a number, magnitude of a quantity by a number in decimal number system in our day-to-day life. We say that our school is 10 kilometers away from our home. The shop is 2 kilometers away from our home. I bought 2 kilo of potato today, like this. So we represent each and every number in decimal number system in our day-to-day life. Similarly, there are other number systems in the variants of positional number system that are used in case of computer language, where the computers can understand only the high and low voltage. They can recognize between the difference between the high voltage and low voltage, or the presence or an absence of charge. There are two states, one is presence of charge, another is absence of charge. The presence is denoted by 1, the absence is denoted by a 0. So such a number system where only 2 digits are used is called a binary number system. The base of such a number system is 2. Like the base of decimal number system, it is 10, where 10 digits are used. There are 10 symbols. In case of binary number system, there are only two digits or two symbols that are used to represent numbers. So the base of a binary number system is 2. So as we move on, as we read the chapter, we will learn that there are other number systems that are used for computer language, for machine language. We use the binary number system and pattern of zeros and ones, which is 8 bits in length, is called a byte, and it is required to represent a character. So there are so many characters on the keyboard, you can see, like the letters, like the numbers, the special characters. Each and every character needs at least a byte to be represented. So a sequence of 8 bits is called a byte, and it is required to represent each character on our keyboard. Now 4 bits is called a nibble. So two nibbles comprise 1 byte. 2 nibbles is equal to 1 byte. Now this representation, you can see 1000 1010 is called a byte. So this kind of representation can be, how many number of representations can be there, which is 10 bits in length. There can be 256 representations. So how do I get the number 256? I got the number 256 by calculating 2 to the power 8. You can see 2, you can calculate in your rough copy 2 to the power 8, or 2 multiply 2 8 times, 2 into 2 into 2 into 2, like this. You multiply 2 8 times, you will get 256. So there are 256 such representations, right? Now we cannot represent, we cannot memorize these numbers easily. Can we memorize 256 representations so easily? No. So to make it a compact one, other number systems are also used, like octal and hexadecimal numbers. We can make this one compact by using a hexadecimal number, where it can be written as, this is equal to 8. 1000 is equal to 8, and 1010 is equal to A. This is 10 in decimal. You will learn how to calculate this and how to calculate this in binary. We will see in the latter part of the chapter. So you will see that this is 8 and this is A. 10 is written as A in hexadecimal, and this is 8. 8A. So the representation becomes a compact one. So for this reason, other number systems like hexadecimal or the octal number system are also used. Mostly the hexadecimal number system is used. So we will see one after the other. So let's read through the chapter and see what are the informations we get from it and what are the concepts we have to learn from the chapter. So we know well that a computer can do calculations very fast, but do we know how it does the calculation so fast? We have learned that a computer understands machine language of 0 and 1. only. Now here we will learn how this 0 and work in a computer. So how this 0 and 1 work in a computer we will see in this chapter. So 0 is represented as an absence of charge, 1 is represented as a presence of charge. So that is how the number is represented in a computer language, in a machine language. We already knew that a computer is a man-made electronic machine. It does not understand the language people use to communicate with each other. Computers recognize only two discrete states, on and off. This is because computers are electronic devices powered by electricity, which also has only two states, on and off. So it recognizes only two discrete states, on and off. So these two discrete states can be represented by two digits, 1 and 0. So like that, 1 and 0 is used to represent the absence and presence of charge. 0 and 1, the two digits 0 and 1 can easily represent these two states. The digit 0 represents the electronic state of 0, absence of an electronic charge. The digit 1 represents the electronic state of on or presence of an electronic charge. When people count, they use the digits in the decimal system. A computer uses a binary system because it understands only two states. The binary system is a number system. So, a computer uses a binary system because it understands only two states. The binary system is a number system that has two unique digits 0 and 1 called bits. A bit is a short for binary digit. Is the smallest unit of data computer can represent. So it is the smallest unit of data that the computer can represent. Bit is the smallest unit of data the computer can represent. When 8 bits are grouped together as a unit, they form a byte. So you have seen when you group 8 bits, 1, 2, 3, 4, this 4 and 1, 2, 3, 4, there are 8 bits called a byte, right? When 8 bits are grouped together, it is called a byte, and 4 bits grouped together is called a nibble. N-I-B-B-L, nibble. So 2 nibble is equal to 1 byte. Okay. 8 bits grouped together as a unit, they form a byte. A byte is informative because it provides enough different combinations of zeros and ones to represent 256 individual characters. These characters include numbers, uppercase, lowercase letters of alphabet, punctuation marks, and others such as letters of Greek alphabet. So how you got this number 256 you have seen? 2 to the power 8 is equal to 256. Why 2 to the power 8? Why 2 and why 8? 2 is because the base of the number system is 2, and what is the length of the bits in length of a byte? It is 8. How many bits are used? 8 bits are used. So for you can see there are 8 different positions in the number. So for each position, how many different combinations can be there? 2. Right? Here I can place 0, I can place 1 also. Here I can place 0, I can place 1. For each 0, for each representation, I can have 2 into 2, 4 representation. Similarly for here, for each representation I can have 2 into 4, 8 representations. For fourth bit, that is, if the length of the representation is 4 bits long, then 2 into 8, it is 16 representations. This will go on. You can see 16 into 2, it is 32. 32 into 2, it is 64. 64 into 2, it is 128. 128 into 2, it is 256. So it is 2 to the power 8, it is 256. You multiply 2 8 times, you will get 256. So there can be 256 representations with a byte. So therefore, it can represent 256 different code, 256 different characters. This code is known as ASCII. Every character in a computer like alphabets, numbers, symbols have an assigned numeric code. This code varies from 0 to 256. This code is known as American Standard Code for Information Interchange. In order to understand the binary system of numbers, we first understand how we form numbers in decimal number system, base 10 number system, which is used all over the world. In the decimal number system, the 10 digits are 0 to 9. Now we will see how we use the 10 digits of decimal numbers to generate the numbers. Then we will see how the 2 digits in binary are used to generate the numbers. Right? The 10 digits are used for a single digit number 0 to 9 it is used. Now, if we want to represent any more item, that is if we want to represent the 11th item, up to 9 we have represented the 10 items. And if we want to represent another item, we have to simply take 9 plus 1. That is 1 will come over here in the tens place and 9 itself will be made here. The next representation will be 1 1, that is 11. Next will be 1 2, 12, 1 3, 1 4, 1 5, 1 6, 1 7, 1 8, 1. After we reach 1 9, we cannot represent the 21st representation, 21st item. We have already represented the 20 items from 0 to 19. Now we cannot represent any more with that. So we have to take a 2, we have to add 1 to the tens place, getting 2, we will get 2 in that way, and we will represent that 9 by a 0. That is, we will get 20. Then again, the next number will be 21, 22, 23, 24, 25, 26, 27, 28, 29. Again, to get more numbers, it will be 30, 31. In this way, we will go on generating numbers like 30s, 40s, 50s till we reach 99. When we have reached 99, we have generated 100 numbers. All the 100 combination of numbers have been generated. No more number can be generated using the 2 digits of decimal, using the 2 places of decimal number. So all the combinations are used to generate the numbers using the 10 digits and the 2 places. Now if you want to represent a more number, you have to use a 3-digit decimal number. That will be a 1 over here and 0 0 in the ones and tens place. Next it will be 101, 102, 103 and up to 109. It will go on in the similar way to and you will generate the numbers in 3 digits till you reach 999. So in this way you generate the numbers in decimal number system using the 10 digits. Now what in binary? How will you generate the numbers in binary number system? You have seen, as soon as you have generated all the numbers using the 10 digits, you need another more place if there is no other combinations left with the 2 places. Like after 99 there is no other combinations left. So you need the next higher place to be filled by 1. Next to be filled by 2. Next higher place will be filled by 3. But in case of binary, when you are generating numbers, you will not get other than the 2 digits 0 and 1, any other number. So you can only fill the positions or the places by 0 and 1. So let's see how they are formed. So if you have only 1 digit, that is 1 bit representation, 1 place, then you can represent only 2 numbers, 0 and 1. Now if you want to represent more than 2, you need to place another 0 over here, take another bit, place another 0 over here and here, by which you will get 0 0 and 0 1. Next you can place 1 over here and 1 over here to get 1 0 and 1. So how many total number of representations you will get? You will get 4 representations: 0 0, 0 1, 1 0, 1. Now 0 is a 0. 0 0 means 0. 0 1 is a decimal 1. 0 0 0 means decimal 0. 0 1 means decimal 1. 1 0 means decimal 2. 1 1 means decimal 3. So how we are getting this? We will calculate. Just after this, after we learn generation of numbers, we will calculate. We will see that 1 means 3. Right? At first, let's calculate. Let's generate the numbers. So 0 means 0, 1 means 1, 10 is 2, 11 is 3. Now you cannot represent any more number like 4. You cannot represent a decimal 4 using only 2 digits, only 2 bits. Can you? No, you cannot, because all the combinations have been used up. 0001 1011. Is there any combinations left? No. So you need to take another place. So place a 0 in the left of this representation. So what will you get? 0 0 0 0 0 1 0 1 0 0 1 1, like this. See, here it is written 0 0 0 means a 0. So when you place a 0 in the left of this representation, you will get this number only, this decimal number only. You are not representing any greater number. But when you place a 1 over here, you will be representing a greater number. The value of the representation will be changed. So 0, adding a 0 to this will keep the representation same. See, 3 means 1 1, you have seen. So 0 1 1 means also 3. Similarly, if you place another 0 over here, then also it will be 3. 0 0 1 1 means 3. 0 0 1 0 means 0 0 0 1 means 1. So it is why you can ask me that why will you write 0 0 0 1 for 1 when you can only write 1 for 1, or only 2 bits are sufficient, 0 1 for 1, because you need to represent bigger numbers. When you need to represent bigger numbers, then you have to represent that 1 also with a bigger number of bits, with more number of bits. Then only you have the provision to represent a bigger number. Otherwise, if you represent a 1 only with 0 1, you can represent only up to 3. You cannot represent more than 3. So to keep a provision of representing more number, a bigger number, you represent that 1 by bigger number of bits, that is 0001 is equal to 1. Similarly, if you represent it with 4 bits, it is 0001. See, here it is done. You can write, here it is not written, you will find it in the table. You can write 0001 is equal to 1. Right. So up to 3 it is clear. Next, to represent a 4, we need a 1 over here and 00 over here, because we have finished all the representation using 2 bits. There are no more representations available. No more representation available with the 2 bits. So we need a 3-bit representation. So you can see 1 over here and make this to 0. So 100 is a 4. 101 is a 5. 110 is a 6, 111 is a 7. Now up to this we have finished all the representations using 3 bits, that is 111. Up to 111 we have finished all the 3-bit representation, 0000 to 111. These are 3-bit representations and these are 3-bit representations. So now if you want to represent 8, you have to take another bit over here on the left of. So here you will have 1 and these bits will be 0. 111 you have to turn to 0. See, 1 0 0 0, it is 8. Next 1 0 0 1, 1 0 0 1, it is 9. 1 0 1 0, it is 10. See, 1 0 1 0, it is 10. If you place 1 over here, you will get a bigger representation. 1 0 1 1, it is 11. 1 1 0 0, it is 12. 1 1 0 1, it is 13. 1 1 1 0, 14. 1 1 1 1, it is 15. So in this way, the same way you use to generate the numbers in case of decimal, you are also using the 2 bits in case of binary to generate the numbers. I hope you have followed. If you have any doubts, any more doubt in generating numbers, you will comment in the comment box. I will try to clear your doubts with another short video for generation of the numbers only. I'll make a video on generation of numbers if you have got any doubt. So comment and ask your doubts in the comment box, right? 2 digits 0 and 1 are used to form numbers. Each place in a number has the value twice the value of the place to its right. We will see this significance of this sentence. Each place in a number has the value twice the value of the place to its right. So as we move to the left, if we write 1 to the left, it will have twice the value on its right. So this one is having a value of how much? 2 to the power 0 into 1. 2 to the power 0 means 1. 1 into 1, it is 1. And this one is 2 to the power 1 into 1. Means 2 into 1, it is 2. So this is twice that of this one. This one is equal to 1. This one is equal to 2. Again you see this one in case of 7. This one is equal to 2 to the power 0 into 1. 2 to the power 1 into 1, that is 2. 2 to the power 2 into 1, the third one. So 2 to the power 2 means 4. 4 plus 2 plus 1 is equal to 7. So in that way, as we move on, we will see that the left of the you see, to get the next place, Each place in a number has the value twice the value of the place in its right. So it is twice the value. It is twice the value. Okay, you will see it in the following examples. Okay, don't worry. Let's come to the examples. You will see. To get to the next number greater than 1, we put a 0 to the right of 1 to get 1 0. Next, we put 1 to the right of 1 to get 1 1. As we have no more digits, we put a 0 to the right of 1 0 to get 1 0 0. Then we put 1 to the right of 1 0 to get 1 0 1. Further, we put a 0 to the right of 1 1 to get 1 1 0. Then we put 1 to the right of 1 1 to get 1 1 1. This way it goes on, right? And the process goes on with the new form numbers. Remember that the numbers in binary system and read the digit read the digit by digit. 10 is read as 1 0 and not as 1101. 10 is read as 1 0. 1101 is read as 1101. It is not read as 1101. So if you are telling this 1101, you are wrong, because this is not a thousand, this is not 100, and this is why this is not a thousand, not 100, and this is not one. So you well understand, because this is not the power of 10. This is power of 2. This is power of 2. So you cannot tell it 1100. This is only a 1. 1101. Right? It will be clearer once you do with the examples. It will be clearer that why you should not tell this as 1101, but we should call it as 1101. Next, see, number system. Computer is an electronic machine that stores data in coded form or machine readable form. Therefore, chapters have to be, the characters have to be represented in the form of electronic pulses. Two pulses that are used to represent basic numbers 0 and 1 are absence of pulse and presence of pulse. Absence of pulse represents 0, presence of pulse represents 1. Before going into the detail, it is essential to have a basic understanding of the number system. There are two types of number system, as I have already shared you, it's already discussed. The non-positional number system used by the early men and the positional number system. In the past, human beings counted on fingers. For counting beyond 10, they used stones, pebbles, sticks to indicate values. This method of counting uses an additive approach or non-positional number system. In this system, we have symbols such as 1 stick for 1, 2 sticks for 2, 3 sticks for 3, 4 sticks for 4, 5 sticks for 5, like this. Each symbol represents the same value regardless of its position in a number. And to find the value of a number, one has to count the number of symbols present in the. So you can understand, you are just counting. See, there is only 1 stick for 1, 2 sticks for 2, 3 sticks for 3, like that. So this stick is same as this stick. This is having a value 1, also this is having a value 1. There is no difference of value with respect to the position. And that is why it is called a non-positional number system. Simply you are using an additive approach. You are counting the number of sticks to determine the value of the representation. The whole representation, you are determining the value of the representation as 3 by counting the number of sticks. So each and every stick having a value 1. There is no other value than 1. So it is a non-positional number system. It is very difficult to perform arithmetic calculations with such a number system. Now you come to positional number system. In a positional number system, there are only few symbols or digits. These symbols represent different values depending on the position they occupy in a number. The computer can understand positional number system when we type some letter or words. The computer translates them into numbers, as computer can understand only numbers, right? You mark this point. When we type some letters, characters, it gets translated to a number, as computer can understand only numbers. There are different positional number systems. These are decimal number system of base 10. Why it is base 10? Because there are 10 digits. You can see 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The digits are let's see, so you know the digits that are used for decimal number system, that is from 0 to 9. It is already written. I think it's not required to write. So it is 0 to 9 means 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. For binary, it is the base is 2. Why? Because there are only 2 digits, 0 and 1. For octal number system, it is 8, 0 to 7. It is 0, 1, 2, 3, 4, 5, 6, and 7. For hexadecimal number system, the base is 16. Why base is 16? Because there are 16 different digits or different symbols that are used in hexadecimal number system. What are they? 0 to 9, as it is used in case of decimal, it is same. And then 10 is written as A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So 0 to 9 and A to F. So there are how many representations? 0 to 15. That is 16 representations, 16 digits, right? You will see this again. There is a tabular form of representation. It is written there, right? So let's just remember that for decimal number system there are 10 digits, so base is 10. Binary number system there are 2 digits, 0, 1, base is 2. Octal number system there are 8 digits, 0 to 7, so base is 8. And for hexadecimal the base is 16, 0 to 15. 0 to 15 is not written as in a similar way. 0 to 9 is written, then 10 to 15 it is written as A to F, capital A to capital F. right? So like that. Next is decimal number system. We first read decimal number system, then we will read binary number system, and then the conversion of binary to decimal, decimal to binary. While converting a binary number to a decimal number, we will understand how to verify the previous representations. We have already written 0 to 15 of decimal using binary, so we will verify that, right? First, see the decimal number system. The decimal number system is a base 10 number system. Deci means 10. The base of a number system indicates how many symbols it uses. The decimal number system uses 10 symbols, 0 to 9. Each of the symbols in the number system has a value associated with it. For example, 3 represents a quantity 3, 5 represents a quantity 5. The decimal number system is also a positional number system, which means that a number such as 123, each position in the number has a value associated with it. What is the value associated with it? It is of the base, right? It is according to the base, and the based on the power, it will be power raised to the base, right? What is the power raised to base? You can see here to here. You will count 0, 1, 2. So in the number 123, 3 is in 10 to the power 0 place, 2 is in 10 to the power 1 place, 1 is in 10 to the power 2 place, right? So 10 to the power 0 means what? Anything to the power 0 is a 1. 10 to the power 1 means 10. 10 to the power 2 means 100. So 1 into 10 to the power 2, 2 into 10 to the power 1, 3 into 10 to the power 0. So 1 into 100, 2 into 10, and 3 into 1. Right? So in that way you get 123 as the sum of the values in each position of the number. Okay. Now you are acquainted with this. Okay. So you will see in case of binary number system, right? Here you have calculated the positions from right to left, 0, 1, 2. This is 10 to the power 0, 10 to the power 1, 10 to the power 2. Similarly, for the binary number 1001, you will calculate like this is 0, 1, 2, 3. This is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Why 2 to the power? Because this representation is in binary number system. This is not in decimal number system. Had this been in decimal number system, we would have written 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3. But this is in binary number system. So for this, we have to calculate the powers of 2. So 1 into 2 to the power 0, 0 into 2 to the power 1, 0 into 2 to the power 2, 1 into 2 to the power 3. So from the right to left, we have to determine the positions first. This is position 0, This is position 1, 2, 3. See, like this. 0, 1, 2, 3. 2 to the power 0 into 1. 0 into 2 to the power 1. 0 into 2 to the power 2. 0, 1 into 2 to the power 3. Now, from here you can see the positions having a 0 in the representation is giving you a 0, because 0 into something is a 0. So for the positions you are having 1, that is giving you a value, right? So 2 to the power 3 is having a 1 and 2 to the power 0 is having a 1. So for that places you are getting a value 8 plus 1 is equal to 9, right? Similarly, if you calculate 1010, you have 1 for 2 to the power 3 and you have 1 for 2 to the power 1. See, 0, 1, 2, 3. This is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So 2 to the power 3 and 2 to the power 1 is having a 1. So 2 to the power 3 is equal to 8 and 2 to the power 1 is equal to 2. So that will make the value 10. So 1010 in binary number system is equal to 10 in decimal number system, and 1001 in binary is equal to 9 in decimal number system. So you have learned how to calculate a binary number, how to convert a binary number to a decimal number. So you can see here is a table given. We will verify each of the binary number, that whether this binary number is equal to this decimal number or not, for each of them up to 15. That would be your task, to verify each of the binary number from 0 to 15 using this. You will see this table. You see, for example, I have taken the examples of 1011. You can see 1011 where it is 1011 here, right? 1011 means here it is written 11. So we will see whether it is 11 or not, right? So let's see 1011. This is a 0, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. See, 2 to the power 0, so written 1 into 2 to the power 0, 1 into 2 to the power 1, 0 into 2 to the power 2, 1 into 2 to the power 3. So as 1 will give you a value, see, it has got 1 in the place 2 to the power 3, 2 to the power 1 and 2 to the power 0. So 2 to the power 3 is 8, 2 to the power 1 is 2, 2 to the power 0 is 1. So 1 plus 2 plus 8, it is 8. So it is correctly written. Again you see 1101, 1101 is equal to 13. So let's verify it is having a 1 in the place 0, 2, 3, 2 to the power 0, 2 to the power 2, 2 to the power 3. So 2 to the power 3 is 8, 2 to the power 2 is 4 and 2 to the power 0 is 1. Anything to the power 0 means what? 1. So, and this 2 to the power 1, here it is 0 into 2 to the power 1 means a 0. So the place having a 0 will give you a 0, right? So 1 plus 4 plus 8 it is 30. I suppose you have understood. You will verify each of this on your own, and if you come across any doubt, you will comment. You will ask your doubts in the comments. Okay. See, the positional number system depends on where the numbers are placed in the sequence of numbers. The non-positional system does not depend on the position of the number, and the symbols are used to represent the number. So non-positional number system does not depend on the position of the number in the representation, and the symbols are used to represent the number. But in case of positional number system, it depends on where the numbers are placed in the sequence of numbers. So if 3 is placed in 100 place, it will be different from the 1 if it is placed in the ones place. Like in the number 123 you have seen, if 3 is placed over here and 1 is placed over here, the representation will be different. It will be 321. It will be other than the number given over here. So it has also the value with respect to the position. Positional values are there, which is not there in case of a non-positional number. Right, that's what it is written over here. The difference between a positional and non-positional number system. Next, this one, up to this you have seen the conversion between a binary number and a decimal number. You have made conversion from a binary number to a decimal number. Right, while verifying this table, you have done this. Now you will also learn how to convert our decimal number to a binary number. After this, after we read the octal number system, we will read that. Let's read octal number system now. In an octal number system, the base is 8. Hence, there are only 8 symbols in the digits. 0, 1, 2, 3, 4, 5, 6, 7. There are 8 symbols. 8 and 9 do not exist in this system. The largest single digit is 7. 1 less than the base 8. Right? Each position in an octal number represents the power of the base 8. Power of the base. The binary representation for the decimal number 74 is this, and octal representation is 112. So we will see whether 112 is equal to 74 or not. Why? What it is written? Each position in an octal number, each position in an octal number represents a power of the base 8. Represents a power of the base 8. So see, as this 112 is an octal number, each position, this is 8 to the power 0, this position is 8 to the power 1, this position is 8 to the power 2. 8 to the power 0 into 2, 8 to the power 1 into 1, 8 to the power 2 into 1. So 8 to the power 2 into 1, 8 into 8 it is, 8 8 is 64. 8 to the power 1 is 8, 8 to the power 0 it is 1. So 2 plus 8 plus 64 it is 74. So this number 112 in octal is equal to 74 in decimal, right? So each position in an octal number represents a power of the base 8 is a power of the base 8. So from right to left, we calculate 8 to the power 0, 8 to the power 1, 8 to the power 2. 2 into 8 to the power 0, 1 into 8 to the power 1 plus 1 into 8 to the power 2. So like that, you can calculate the octal number also. You can calculate the value of the octal number and get the decimal number, value of the octal representation in decimal. So that is how you convert an octal number to a decimal number. Okay. So the decimal equivalent of octal number 112, again you see, you cannot tell this as 112. You have to tell this as 112 because this is not 100, this is not 10, and this is not. So it is an octal representation. In case of decimal representation, you used the number to be as 112. Right? It is not 112 in case of octal representation. Okay. The position is 8 to the power 2. This is 64. 64 into 1. Right? This is not 100. This is something less than 100. Yes? So it is 112, not 112. The decimal equivalent of octal number 112 is equal to 74. See, I am telling this as 74 because this is in decimal to the base 10. Right? Now, since there are only 8 digits, 0 to 7, octal number system, in octal number system, 3 bits are sufficient to represent an octal number in a binary system. 3 bits are sufficient. See, 3 bits are used. Can you see? 3 bits, 1, 2, 3. 3 bits are sufficient to represent an octal number. So 0 is written as 0, 0, 0. 1 is written as 0, 0, 1. 2 is written as 0, 1, 0. 3 is written as 0, 1, 1. And this way, up to 7 it is written as like this. So you have already seen that up to 3 you can see up to 3 it is all 0 on the third place. So you can well represent 0 to 3 with 2 bits, only with 2 bits. But as you need to represent 4, 5, 6, 7 also, you have taken a 3-bit representation for the digits. Right? So you have to take the greater number of representation, the minimum number of bits you need to represent the maximum digit, maximum value of a maximum value you want to represent. So maximum value you want to represent can be represented by a 3-bit representation. So you have taken a 3-bit representation for each of them. Right? I hope I am clear. 0 to 3 can be represented using only 2 bits. But you have taken the 0 on the left so that you can take a 1 on the same position for the rest of the representation where you need a 1 to represent the remaining digits of octal. So the highest digit, that is 7, can be represented using 3 bits of binary. So you have taken 3 bits. So you have already verified. See, you can verify again. This is in binary 0, 2 to the power 0, 2 to the power 1, 2 to the power 2. So 2 to the power 0 is 1. 1 into 1 it is 1. This is 2 to the power 0, 0 into something, it's 0 only. 1 into 2 to the power 1, it is 2. See this one, 2 to the power 0, it is 1 plus 2 to the power 2 to the power 1, 2 to the power 0, 2 to the power 1. The 1 into 2 to the power 0, it is 1 plus 1 into 2 to the power 1, it is 2. 2 plus 1, it is 3. Now here it is having 1 in the place, 0, 1, 2. 2 to the power 2. 1 into 2 to the power 2, it is 2 to the power 2 means 2 into 2, it is 4 into 1. 4 into 1, it is 4. And rest of the place is having a 0. So it is 0. Again you see 1 into 2 to the power 2, it is 4 plus 1 into 2 to the power 0, it is 1. 2 to the power 0, anything to the power 0, it is 1. 1 into 1, 1, and 2 to the power 2, 4. 4 plus 1, it is 5. Here 2 to the power 2 plus 2 to the power 1. 4 plus 2, it is 6. Here 2 to the power 0, to the power 1, 2 to the power 2. 4 plus 2 plus 1, it is 7. So like this, you have already verified the values here. If you have verified the values over here, you will have no problem in verifying the values over here. So these are the same values written using only 3 bits of binary. Okay. Now it's time to see how a binary of triplets, binary can be made into a triplet and made to a corresponding octal number. With this table given below, each digit represents 3 binary digits. In the given table, it displays that in an octal format, each digit represents 3 binary digits. It is easy to translate octal and binary. You can see 3, 7 in octal. So what will you write 3, 7 in binary? 3 is written as 0, 1, 1. 7 is written as 1, 1, 1. So 3, 0, 1, 1. 7 is written as 1, 1, 1. Right? So 3, 7 is written as 0, 1, 1, 1, 1, 1. Right? 5, 1 in octal is written as 1, 0, 1, 0, 0, 1. 1, 0, 1 and 0, 0, 1. So if you memorize this whole table, you will have no difficulty in having a conversion, to convert from one representation into another. So octal to binary, right? Octal number system to binary number system. So let's take an example, 425. You cannot tell 425, is 425. 425 in octal is dash in binary. If the question is like this, what will be your answer? Your answer will be 100 for 4, 010 for 2, and 101 for 5. But you will not say like this. That is your calculation. You have to write it all together, right? 100, 010, 101. If someone gives you 7, 3 in octal, what is the binary? It is 111, 0, 1. Like 6 5 in octal. 6 is 110, 5 is 1010. So in this way you do the conversion. If you memorize the table, you do the conversion easily. Okay, next is hexadecimal number system. We will continue with hexadecimal number system in the next video, right? So comment your doubts. Let me know your doubts so that I can clear it in my next video. Thank you all.